So I put in with images in a task because I wanted, maybe you can do the results like this. It will be really nice if you can do something similar. It means that you need to create, it's not really important that it will be the same, but the best way to do it, if you can make a 3 figures. So 3 figures, in all of the figures, the top graph is not changing. So it's an analog signal from the task number 1. You're just creating the analog signal, putting as much values as it can to imitate the analog signal, and in all the figures it stays the same. Another graph in the bottom of figure, so it's the digital signal, and we're showing how this digital signal is changing when we changing the sampling rate. And at the beginning, let's try, I hope for everybody it's clear, but about that Nyquist frequency. Maybe you can find information in the internet, and maybe you are a little bit misunderstood what is this Nyquist frequency actually is, because there is a few terms: Nyquist frequency, Nyquist rate, and all these terms is talking actually about the same thing, but maybe from the different perspectives. So the main idea, it's a Nyquist theorem, and is talking about that when you need to decide the correct sampling rate for signal, you need to look what is the biggest frequency of the signal which you need to digitalize, which you need to sample, which you need to make digital. Yeah. So in this case, 10 hertz is the biggest. It's bigger than 3 hertz. So 10 hertz is the biggest frequency which we need to sample. And this theorem says your sampling frequency needs to be twice bigger than your highest frequency which you need to sample. So in this case, Nyquist sampling frequency will be 20. Or this theorem saying that this Nyquist frequency needs to be not equal twice bigger, but a little bit bigger than twice. So maybe you can use not 20, but 21 will be enough, because it's a little bit bigger than twice. Yeah, so when you look to your task, you just need to view what is the biggest frequency which you need to sample, and when decide what is your Nyquist frequency, and make this graph with the Nyquist sampling frequency, later one graph with a lower one Nyquist. So in this case, you can choose sampling frequency 15 and sufficiently high. So it means that really high to make the same signal as it analog. So it can be 100, 150, and so on. You can. So I can show you the also maybe some like example how to quickly do it. Yeah, so if you're, let's now think if I just will make a fantasy about 5 and 10 hertz, for example, and our audio meanings is, let it be sinus 2p f1 t plus cosine f2 And also we need to create the time vector here, yeah. For example, 1 second, let it be, and here. Let's put in an analog graph, at first you need to create as much values as you can. That, yeah, it's digital signal, but you need to imitate that it's an analog signal, and it has all the nice sinusoidal view and not any corners and so on. So if you're now trying to plot this one, let's look how it looks like. Okay, we have a signal like this, and now what we want to make the subplot, and to have it in one figure, this graph always in a top view. And now we will make the digital signal. So we will make the same function. Let's think that it's a y2, and we need to make new time vector. Yeah, which is actually now will be dependent with a sampling frequency. So do like this. And now we will change now the sampling frequency. Now let's try that Nyquist theorem. And here, of course, because we have time 2, so let's put here a time 2. And let's try to plot, also subplot. Okay, yeah, sorry, but at first we need to actually stem, because it's a digital signal. And what I'm showing here about this image, in a stem graph, you will get only the points of digital signal, yeah? So you will get the view like this. Yeah, and it will be clear to see the results if you just try to write the lines between these points, yeah? So the easiest way actually is just to use function hold on and make the same graph with a plot. So the result will be like we just show the lines from the one point to other point. The result is like this. So here actually you see that here we're showing the Nyquist frequency sampling rate. It means that we're not losing any points of signal. So here is the example how a signal looks when we sample it with a Nyquist frequency. So the theorem says that it needs to be a little bit bigger when twice. Let's try how it looks now. Okay, after that I need to shoot off, hold on function and write hold off. Yeah, you just need to experiment a little bit. Maybe in your case, in your task, that twice bigger sampling frequency, it is better. Because now you see when I'm making the sampling frequency bigger than twice, I get a little bit not so good results. So it is because now we're analyzing only short term of signal, and we have here only not so much points. Yeah, so in this case, this theorem that it needs to be bigger than twice, maybe not exact true if we will analyze the long audio audio information segment. So maybe the results will be better if we use bigger than twice. But you just need to analyze, experiment. Maybe just twice the highest frequency will show you the good results, or bigger than twice, but something around here. So let's look one more time with a twice one. So here is the good results. If you can do like that, your signal, it will be nice. And lower than Nyquist frequency, if you make something lower than 20, you will have the results. Here actually it's not so bad still, but so you can also show the results which is really bad, and it's okay, and it's really okay. You just choose that sampling frequencies which looks better, or better represents the Nyquist theorem. So for example, now if I make the sampling frequency really low, as you see, so now I really lose the signal. Let's try 12. I think it's a good view now that we lose this point of signal, we lose this point of signal, and this point of signal we don't have, and so on. So, for example, here is a good sampling frequency, how we can show that we need to think about this Nyquist theorem, yeah? And 20, it's a good view of Nyquist theorem, that we saving all the signal values. And for example, later you can just make really big sampling frequency and show the good results where we have all these nice sinusoidal things, all these round corners and everything. So actually it's everything for the task number 2. You just need to change this number and you will get everything what you need.